Okay, guys, let's look at some ellipses and some cool facts about them. So, first thing about an ellipse, it says, if a source of light or sound is placed at one focus, the waves transmitted reflect off the ellipse and will concentrate at the other focus. So one cool thing that happens here, right? Here's one focus. Here's the other focus. Anything you put at this focus will shoot out, reflect off the surface of the ellipse, and bam, hit that other focus. Any direction. Even if it goes away from the other focus, even if it goes this way, it's going to hit there, and it's going to reflect back that way, right? So kind of crazy, pretty cool characteristic of ellipses here. Now, one really cool thing is called a whispering gallery. Let me show you the picture here first. So what happens in a whispering gallery, and there's a few of these, I think one's at the Museum of Science and Industry. This was actually a scene in the show How I Met Your Mother. If you're a fan of that show, it's a pretty funny scene where one person's standing in a whispering gallery at one focus and one person's at the other, and they hear some things being said. So what happens is if you stand in a room here, and you have a friend standing in the room over here, and one person whispers, what happens is the sound waves hit off the elliptical ceiling and go back to the other person. So you can actually hear someone whispering. You know, I can't be too loud in the room, obviously, but if you whisper quietly from one side of the room, even though you normally wouldn't be able to hear the person, right, in a flat-roofed building, because it's an elliptical roof and the sound waves reflect and focus on the other focus, you can actually hear the person pretty well from across the room. Now, you won't believe it. You'll think that, you know, there's some microphone or something going on, but it's not. It's just properties of conics. So let's try an example here. In a whispering gallery, Jim is standing at one focus and is 6 feet from the nearest wall. His friend Bob is standing at the other focus 100 feet away. Okay, so let's try to set this up. Now you're going to see this set up in different ways. You got to read the problem carefully and see what's going on. Jim is standing at one focus, so let's say Jim's over here, okay? And we know that he is 6 feet from the nearest wall. So if this is the wall over here, we know that he's 6 feet in this way, right? 6 feet in, okay? Now, the next thing we know is it says that Bob is 100 feet away. So we'll say Bob's over here. And this distance here is 100, okay? So now 100 feet. Again, just like parabolas, we get to pick where we put everything. For parabolas, we put the vertex of the parabola at 0, 0. For ellipses, I'm going to put the center at 0, 0. Again, that eliminates the h and the k from the equation. So here is my center, right? Now, with this whispering gallery problem, there is another piece of we're only dealing with half the ellipse. The other half of the ellipse is down there. We really don't care about it. It's underground technically, right? So that's all we care about now. There's the top half of this ellipse. Now, if they're 100 feet apart, kind of like the parabola examples, that means that we know that this point here is 50, 0, and we know that this point over here is negative 50, 0. All right. Now, we'll talk about what that's given us here in a second. Now, remember with the other part, Jim is 6 feet away from the wall. So that means that this point out here, right, at the tip, is 50 feet here plus another 6. So that's going to be negative 56, 0, right? Now, because his friend, Bob, is standing at the focus, we can also label this. We know that he's going to also be 56, 0, right? Remember, ellipses, parabolas, everything in conics is all symmetrical. Okay, so there's the setup. The question is asking a few different things. Let's number one, what is the length of the whispering gallery? So once we get the picture set up, we can see that the length from edge to edge is 56 plus 56, so that's 112 feet. Letter B, how high is the elliptical ceiling at the center, right? So what that's asking for is the height. That's another way of saying the B value, right? So what we have here, we have 3 values so far. The distance from the center to the focus, if you remember back from our lessons on ellipses, that is the C value. So we know the C value is 50. The distance from the center to the edge is 56. That's our A value. That's the A value. So then I can use those two to find the B and this little equation, right? Remember, C squared equals A squared minus B squared. So I plug things in. I get 50 squared equals 56 squared minus B squared. And I can clean this up. If I solve for B squared, however you want to do it, I'm going to add the B squared over, and then I'll subtract the 50 squared over. And now you can go to the calculator. You're going to get some big number here. You're going to have to square root that number when you subtract those two, and you'll get 25.22 as your B value. So let's go back and answer the question. How high is the elliptical ceiling? It's 25.22 feet. All right. So that's it. Again, in this one, I did not have to find the equation. I just had to identify the A, B, and C values. And usually for these applications, you'll have to find one of those. Sometimes you'll have to find the equation. Sometimes you'll just have to find an A, B, or C value. Okay. Let's try another problem. This one is another bridge. We saw an application of this with parabolas, right? That said a parabolic bridge. This one says a semi-elliptical bridge. So be careful there. You get slightly different answers if you use the wrong equations. So this one says a bridge is built in the shape of a semi-elliptical arc. The bridge has a span of 60 feet. The maximum height from the water to the arch is 20 feet. It says find the distance from the water to the top of the arch at a distance 20 feet from the center of the bridge. Okay, so to set this one up, I have a picture there just so you can kind of visualize what's going on. And I'm going to draw it over here. Remember, it's always easiest to put the center, for center of ellipses, vertices of parabolas at 0, 0 if you can. That's why I drew this the way it is. Now, just like the last problem, the other half of this ellipse is underwater. So you don't have to draw that unless you want to. But this is what I'm dealing with. Now, it says the bridge has a span of 60 feet. So like all the applications we've seen, that means it's going to go 30 each way. So 30, 0, and negative 30, 0, right? It also says the maximum height from the water to the arch is 20 feet. So that maximum height, the water is down here on the x-axis. So the maximum height here is 20. That means this point up here is 0, 20. All right. So what I'm getting here, just from the setup, is that the A value is 30. The B value is 20, right? Now, you might have to find the C. I don't see anything in here talking about a focus, asking for a focus. So I'm not going to find the C right now. But what I can find is the equation. X squared plus y squared equals 1, right? I have to put because this is a horizontal ellipse, the A value, the A squared is going to go under the X's, so 900, that's A squared. The B squared value is going to go under the Y's, that's 400. So that is the equation that describes this ellipse. Now look what it's asking. I want to know find the height from the water to the top of the arch at a distance 20 feet from the center. 20 feet from the center. So we go from the center. Now I could go 20 each way, right? I could go 20 this way. I could go 20 the other way. It doesn't matter. It's symmetrical. So let's say we go 20 this way. Go 20 that way. I want to find, that's 20. I want to find, and I think we're in feet. Yeah. So 20 feet to the right. I want to find the height of the bridge. Okay. So kind of like one of the examples we did earlier, this is code for finding the y value. That's it. Now, whenever I need to have an x value and I need to find the y, or you could have this flipped. I could give you the y value to ask you to find the x. You need an equation, which we found. So what I'm going to do now is when x equals 20, I'm going to plug 20 into the equation. So 20 squared, using this over here, over 900, plus y squared over 400 equals 1. And now you're just going to solve for y. Now this is a little more complicated than solving the parabolas. not much. You get to use the calculator. I really wouldn't use that until the end, unless you can use it as you go through. So if you type this in, 20 squared divided by 900, that's going to be 400 over 900. That's just 4 over 9. So you could keep, again, like always, we don't use the calculator to the end, but if you want to get sick of writing big numbers, you can see if those reduce. Plus y squared over 400 equals 1. I'm going to subtract the 4/9 over, so I get y squared over 400 equals 5/9. Now, up to you how you want to do it from here. Probably on the calculator, I'd multiply both sides by 400. I'd square root both sides. I'll show you the work. If you just multiply both sides by 400, you get 2,000 over 9. Now, if you square root it, you get a y value of approximately 14.91. So there is the height. When you go 20 feet from the center, your y value right here is 14.91 feet. All right. So those are two good examples of our ellipse extensions combined with the two parabola extensions, two examples we did. Your homework for this is on my lab math. It's called Applications of Parabolas and Ellipses. As always, pop into the office hour if you have any questions.